Okay, thanks everyone for joining. This is the reading group. And for this week, we read the article on local aggregation for unsupervised learning of visual embeddings. And the authors are Zhuang Zhai Yamens from Stanford University, and Alex Tsai and I will present this work. So generally, like learning algorithms are divided into supervised and unsupervised learning. And supervised learning works on a specific data, and it needs a lot of labeling, which is a laborious task and is expensive, but it gives us a good performance, and it's normally now used in the real world. On the other hand, the unsupervised learning, which is the more human-like learning, and they're suitable for the general purpose AI, they learn the similarities in data and they categorize the data by themselves like naturally. So they can work like on unlabeled raw data. But they have like a relatively low performance now, and they have limited usage in the real world. So this article focuses on developing an algorithm for unsupervised learning to improve the performance of the state of the art using a local aggregation method. And they are focusing on the visual embeddings. And what they do is that they first embed the inputs into the lower dimensional space via a neural network, and then use those embedding space where at each optimization step, they identify neighbors surrounding each example in the embedding space. And also then they define a new loss function where they call it local aggregation metric, basically. And what that does is that they group the images based on their similarities. So the similar features will be grouped together, and they will form some sort of clusters. So now let's first look at how do they how do the neighbors identification and what is their algorithms. For neighbors identification, they use two groups of neighbors. They call them background neighbors and close neighbors. Background neighbors are denoted as B, close neighbors denoted as C. And background neighbors identification is basically where it's a nearest neighbors identification, where you find the distance of an embedding based on a specified cosine distance from all the nearest neighbors. And that specified cosine distance, you can think of it as a cutoff distance. So now let's go through this like one illustration of that, like using a simple examples to better understand how does the background neighbors identification work. So we have this embedding space V, which consists of 7 images, V1 to V7, and they're randomly distributed in this space. And then if we have some specified cosine distance, then we calculate the distance of V1, and we are interested in the background neighbors of V1, let's say here. And we calculate the cosine distance of V1 from its nearest neighbors. We get V3, V4, V6, and V7, which are shown as the blue images here. And they are identified as the background neighbors for that image V1. And then close neighbors identification has several more steps, where we first cluster all the embeddings into the groups using k-means clustering. But since the k-means clustering is a noisy process, and normally the clusters that it gives us is not that accurate, so we need to repeat that k-means clustering several times to improve the accuracy. And then for each k-means clustering, it determines the group of each embedding. And at the end, the way the close neighbors of a specific embedding is determined is by getting the union of the groups from each clustering, from each k-means clustering that is done. So now if you go through the example, I think all this will make more sense. Also, let's look at the embedding space that I've already shown you. So now we can k-means cluster all the embeddings. You see that the embeddings are now grouped into the 5 groups, G1 to G5. And once we have that, for example, for the embedding V1, its nearest neighbor or its close neighbor will be V3, which are in the same group of G2. So far we have determined that group for the V1. And then if now, according to algorithms, we need to repeat this k-means clustering several times to get a better group of close neighbors. So now we do another k-means clusterings, and this time also with 5 groups, but it does not have to be 5 groups. Actually, the number of groups that you use in the your k-means clustering, it's a hyperparameter that you can tune. In every time that you do k-means clustering, they can be the same for convenience, or you can like slightly play with them to change them. But you will come up with another set of 5 groups, as you can see here. And this one, the close neighbors of V1 will be, for example, V7, and the group is now G5, which I've highlighted here with the red dash dots. And then at the end, let's say we have done so far 2 k-means clustering, each time with 5 groups. And also the number of k-means clusterings that you do is also a hyperparameters, in addition to the number of groups that you use in your k-means. So now if we get the union of the 2 groups that we got from each times we did the k-means clustering, we will get the V3 and V7 as the close neighbors of V1. And this is what the algorithm basically does, like to determine the close neighbors of the an embedding. And this is one of the examples that they have shown in the paper, where they determine some of the successful and failures in neighbors identification. For example, these successful images, you can see that in the zebra, they have found it in the similar images, where from left to right, the distance is increasing. And these are some of the failures where the nearest neighbors doesn't look like the like an original image. And then they have also shown the results in an embedding space using a scaling visualization algorithm, where you see this embedding on the left is a high accuracy, where all the clusters are like the same colors, meaning that they're like very similar features. For example, the yellow ones, you see that they're all clusters together. But the low accuracy, the colors are more distributed, basically. You see the yellows are more distributed all over the embedding space. And for example, this trombone, like it's here and here, even in 2 different contexts, but they're not grouped together. And they have also looked at the validation performance of ResNet 18 for different choices of background and close neighbors. And they found that generally by increasing the number of groups you use in your k-means clustering, and also the number of times you repeat the k-means clustering, the performance is improving. And I think that's on my side. So from now, like I pass it to Alexei. He will talk about the local aggregation metric. I can stop sharing.
Yeah, hello everyone. Can you see my screen?
Yes.
Yeah, so local aggregation metric, basically authors use that for measuring the performance of the model of the local aggregation algorithm. And basically it's just negative log function. And here you can see that in numerator we have probability that the image is the closest neighbor and the probability that the image is the background neighbor, and in denominator we have probability that the image is a background neighbor. So basically, in order to minimize the loss function and get better results, we need either to minimize probability that the image is the closest neighbor, which means that our image is moving farther from the closest neighbor, or we should maximize the probability that our image is a background neighbor. And we just plotted this aggregation metric in order just to visualize how it works. So here you can see that the less probability that the image is the closest neighbor we have, the less loss, the less value of loss function do we have. So basically, in order to get like 0, we need to minimize our probability that the image is the closest neighbor to 0, or we can just maximize the opposite probability that the image is the background neighbor. So here you can see the example from the paper as well about the local aggregation, but this is what Hossein already explained before, but based on just the real image. So here you can see that on the input, we have an example of image, which shows on this embedding space by red dot. So after it goes through convolutional network, it it goes to the embedding space. So here you can see that this image in the embedding space is moving. So it's moving toward to the closest neighbor, but away from the background neighbors. And this is how the groups are creating. This is how the clusters are creating. And after the optimization, we've got local groups of images that have similar features. So basically, all of them, they are closest neighbors. And speaking of the results, authors of the paper, they did three types of tasks in order to measuring the results of the performance. And they did object recognition, scene classification, and object detection. So object recognition answers the question, what is the object in the image? And what did they do? The authors just took all existing architectures like ResNet, ResNet 18, G16, and AlexNet, and trained them by using local aggregation methods. And you can see that best performance. So first of all, we can see that local aggregation method shows best performance at other methods in supervised learning. So best results we've got on ResNet 50, and it's 60.2, which is 6.2% higher than the state of the art. So next task was scene categorization, which means that the model tries to identify what is it seen on the image. And first of all, the conclusion was that the model shows strong generalization ability. And the best performance they've got on ResNet 50, and it's 50.1%, which is also much higher than the state of the art. And in object detection task, which answers the question, where is that particular object on the image, they've got the best results. So they outperformed state of the art and got 69.1% accuracy, which is quite fascinating, I think. So, and as a conclusion, we can say that local aggregation trained models, well, first of all, they classify images quite efficient and regardless of background and viewpoints. Second conclusion is that they can recognize high-level visual context, and in failure cases, there's also like the room for improvement, but authors said that maybe their model misclassified this images in failure cases, not because the model is bad, but maybe because the ImageNet category labeling is not that suitable for unsupervised learning because it labels each image only by one label or only one particular category. But in unsupervised learning, it can be used for like, one image can be categorized for different categories. So that's it. Thank you very much for your attention. If you have any questions, please.
Yeah, hi, this is Jamie. Quick question. So for the local aggregation, the optimization, is that a trained neural net or an algorithm? Or did the paper talk much about it?
Alexei? Alex? Jamie, can you repeat your question? So if Alexei does not,
Yeah, sure. And you know, I have no problem going back to the paper if I need to. So for the local aggregation approach, the optimization where, you know, you show the loss function, is that a trained model or is it just an algorithm that gets you the output from that optimization?
no, they train the model again too. They hyperparameter tune the model as well, but they use the same architecture as the ones like they are in the literature.
Gotcha. Okay.
Hi, I have a question. First of all,
Yes.
I want to say that I appreciate that you guys produce graphics that I didn't see in the paper because it made it easier for me to understand the process a bit.
Of course.
Did the authors mention anything about how they will take this into this approach to the future, how they can improve it? And also, did you happen to see if they have some open source code?
Mm-hmm. Yeah, I think in terms of using this for the future, first of all, authors, they want to improve identification of dissimilarity data. They also want to apply local aggregation for like other classification tasks such as video and audio signals classification. They also want to, well, they declared that they want to do some sort of comparing comparing local aggregation algorithm with biological vision systems and show that it's similar to them. And in terms of source code, yes, they have the code for the paper, but I think, well, I think you can actually like have a look at this if you need a link to the GitHub for this paper. We found that, and yeah, I think we can send it to you.
All right, thanks a lot.
Yeah, I can see